Thank you very much for coming to my presentation. It's really an honor to be here to share my work with you. So this is joint work with Hanjin Kim from INSEAD. We're going to talk about how machine predictions is going to have an impact on not just decision-making itself, but also how it impacts causal explanations that are able to be offered by managers. So there's been growing interest in investing in artificial intelligence. Part of it is powered by automation, but a major part of it is people trying to look out for ways to use artificial intelligence to aid decision-making. So there's been growing research into whether it is possible to automate and augment decision-making, especially managerial decision-making using predictive algorithm, and whether it is possible to essentially improve the decisions. And we find mixed results. Sometimes the decision-making aids can contribute to better managerial decision-makings. A lot of time, it doesn't really realize the potential that it promised. And we think that partly this is because algorithmic bias, but also it could be because of algorithm aversion. But there has been limited research into, in addition to this impact on decision per se, how is this going to change the way that decision makers develop and explain and communicate their decisions? So why are managerial explanations important? Because we really need to not just make a good decision, but be able to explain it to key stakeholders in order to get their support. That includes, for example, explaining why you're making an acquisition to the employees, to investors, to other stakeholders in order to make it possible. And also managerial capability. The essential part of managerial capability is about forming a logical framework about what factors contributes to a better, sustainable, competitive advantage. So this causal logic was behind good managerial practice and managerial theory. So the research question of this project is, how do machine predictions essentially impact decision makers' capability to make good causal inferences and explain that to stakeholders? There's been substantial theoretical ambiguity. On the one hand, we think that by delegating some task, especially the decision-making, the prediction task to algorithm is going to free up valuable cognitive capabilities so that people can focus more on developing complex causal theories. And also, algorithmic predictions can promise to reduce uncertainty, improve the prediction quality per se. But on the other hand, we also worry that people might essentially slipping on the wheel, that they were over-relying on the algorithm, that they do not think through this problem as critically as they should be, so making less effort. Also, in addition to that, it could also be traced back to this idea of multitasking nature of the managerial practice, and by delegating a certain part of the decision-making rights and decision-making task to the algorithm, is going to induce excess modularization of the decision-making process, so that the managers could not think through the whole process from in a holistic way, and they will have a hard time grasping the complexity and the interaction between all of the factors. And there has been limited empirical evidence because it's really challenging to not only observe all of the causal explanations being offered by managers in an organization, it's also very challenging to measure it. So in this paper, we had this unique opportunity of collaborating with a firm who co-designed a field experiment where we randomize providing managers, key decision makers with predictive algorithmic aid, and keep track of how their decision-making process, their causal explanations change over time. So that is a leading financial research firm where they hire hundreds of mutual fund analysts to forecast the performance of mutual funds globally, make recommendations, and most importantly, offer justifications and explanations of why they think they recommend a mutual fund or not. So, in a nutshell, what we find is that even when the algorithmic predictions improve decisions, they may worsen the causal explanations. There seems to be a trade-off. So, and this especially impact the newer, the less experienced analysts' capability to offer good explanations. And it varies. There's some heterogeneity depending on the decision complexity itself. Yes, please.
Just a clarification, when you say worsen, you mean worsen humans' perceptions of those causal explanations or some objective measure?
We construct 3 different measures, both subjectively and hopefully objectively. I'll get to that in a minute.
Thank you.
Yes. So depending on the complexity of the task that they're undertaking itself, we might see some different directions. I'll get into that. So this is what the empirical context will look like. The analysts were assigned lots of mutual funds based on their specialization, and they regularly update it based on the new information available to them and to the investors. And in addition to offer a recommendation decision on a rating scale, they would also provide an analyst report that's very detailed and offering all of the supporting evidence that they collected during their qualitative and quantitative analysis, their research. And then before this analyst report and their decision were published, they go through a very intense internal review process where a committee of internal experts would offer them advice and also rate them. So we asked them to be rated by the analyst committee on a scale of based on their quality of their inferences, based on how clear they are with their causal explanations, are they really grasping this causal model? So, and also, we take advantage of the heterogeneity in terms of the complexity of the task itself and the variance of analyst experience, which range across 30 years. Okay. Some of the key decisions that we care about, the constructs, the outcome that we care about. First of all, we did a manipulation check by seeing whether being offered a predictive algorithm as a decision-making aid is going to change the likelihood that people alter their decision. And also, we care about, is this going to contribute to a higher quality of decision, and we measure the quality of the decision by the predictability of the recommendation of the future fund return. So following the finance and accounting literature, we constructed the risk-adjusted return of the analyst's recommendation of the mutual fund following the Fama-French models. And per your question, we also capture the explanation quality through 3 different methods. First of all, the internal committee is like an expert review of how good that causal framework is. In addition to that, we ask the analysts to self-report a number of decision drivers they identify that contributes to the quality. And the number of causal drivers, as we will see later, is actually negatively correlated to a high quality explanation, because you can imagine that someone who does not have a good framework may provide you with a laundry list of decision drivers. That's suggesting that it cannot identify the key decision-making drivers. Whereas a really concise and well-rounded story would center around a couple of key decision drivers. And we also see that in the baseline data. In addition to that, we also use NLP methods to analyze the analyst reports themselves along the dimension of readability, coherence, the length of it, and also identify the number of causal statements using large language models. Okay, at a baseline, it seems like the more experienced analysts tend to give better, higher quality explanations. And we also see that consistent with our theory that causal drivers have a negative correlation with the causal explanation, suggesting that a high quality explanation usually is very focused on a set of key decision-making drivers. And we also find that, consistent with the previous statement, that the number of causal statements is also negatively correlated with the quality of the causal explanations. And at a baseline, we see some weakly positive correlation between the quality of the decision in the form of its predictability of the future return, and the causal explanation suggesting that it is positively related, but there is some nuance. So higher predictability doesn't always mean a better explanation. So we designed a randomly NRCT across all of the mutual fund manager at this site for a total of 9 months, and we randomly assigned half of the analysts to be powered by this algorithmic prediction tool, and so the control group would continue to do their research on this platform as usual, whereas the treated group would get additional banner information about the algorithmic recommendation of what kind of decisions that the algorithm think they should make. They are not forced to take this advice. Is this their own? They have the right to decide how much they want to incorporate this decision. It could, the algorithm can also recommend them to change the rating to a certain degree. For half of the treated group, we also offered additional information that enhanced explainability of the algorithm. So, and we used the definitive model to leverage the baseline data that we collected. In a nutshell, what we find is that indeed, that junior analysts are the most affected, and the junior analysts, when they analyze the simpler funds, they do experience an improve in terms of decision quality in the form of predictability of future return, but at the same time, their reasoning quality plummet. And we can also see the shift of distribution among the new analysts when they make simpler decisions. Okay, so why is this happening? So we offer some suggested evidence for the mechanism. We think that the analysts, especially junior analysts, tend to over-rely on the algorithm when it comes to the simpler decisions. And it seems like they are shirking a little bit. They are writing shorter, less technical, and less coherent explanations around the decision that they make. And also, they're having a hard time identifying the key decision-making drivers behind their decisions. So I'm gonna, in the interest of time, I'm gonna skip that. These are the NLP methods results that suggest that people are indeed shirking when it comes to simpler decisions. So to recap, we identified a trade-off between higher decision-making quality and better causal explanations, and this is especially problematic for newer analysts. And I think that this is going to have a long-term impact because what this is suggesting is that people might not be conducting on-the-job training as ideally as we want them, that they were essentially not getting the skills, the critical thinking skills that we hope them to accumulate over time because they're over-relying on the algorithm. Okay, thank you very much. Okay, open for questions? Or?
Do we have time for questions?
Go ahead. Yeah.
I've seen a number of papers recently that sort of suggest that explainable methods, in SHAP in particular, are not working in the field. I'm curious as to what you found.
Here we do not see the explainability assessment in the form of SHAP value really contributes to a higher decision-making quality, but we do have some supportive evidence that shows that people trust it. So we have a scale, a self-reported scale of how much do you think the algorithm is reliable? How much would you consider incorporate the algorithm into your decision making? So senior analysts particularly, who have like really low baseline trust of the algorithm, report a much higher use in terms of trust and contribution of the algorithm with explainability.
Thank you.
Is there an opportunity to look at long-term impacts? This is what most people would care about, is that maybe the analyst could make a better decision this time, but they don't really learn the skills they need, therefore their future decisions. So is there any ability to do a longitudinal study here?
Yes, we are definitely trying to look into that. So soon after this, this experiment, the company rolled out the algorithmic prediction as a decision-making aid to all of the analysts, and we're keeping track of, does it have any long-term impact? Do we really see that a junior analyst is essentially not grasping the scale?
Okay. Thank you.
That could be detrimental.
Thank you.
Thank you.
Thank you.
Hi everyone, thanks for coming. I'm Kevin, I'm a PhD student at Booth, and today I'll be talking about how to use language models with A/B tests to make better decisions. This is joint work with Panayotis at Persado and Sanjog, also at Booth. So the motivation for this project is broadly data-driven decision-making, where companies or organizations will make decisions, record data on outcomes resulting from those decisions, and use that data to make better decisions in the future. So, for example, a company might care about what product features do people like the most, what price should we charge for a product, and how should we promote a product. So all my examples are from marketing, but you can think of other ones. And how they might answer these questions are A/B tests. So for the price example, you might test several prices and then pick the one that maximizes your profit. Yeah. But you can do a little bit better. If you fit a demand curve to the prices that you record data on, then you can solve for the profit maximizing price. And that lets you extrapolate outside of things you explicitly test. But that approach doesn't work so well for high-dimensional problems, decisions, like how should what visual appearance of a product is most compelling, or how should we promote a product? Like what text on an ad maximizes engagement? So even if you have a predictive model for those types of decisions, it doesn't tell you how, like explicitly what decision you should make. So the best you can do in those settings is a human still has to input, here are some ideas I have, and they use this predictive model to sort through their ideas. But it's not directly constructive. So this project is about how to use generative models to do this in a more systematic way. And again, I'll be primarily using marketing examples, but you can substitute in something else that you think is more interesting to you. So the old approach, again, as I said, train a predictive model, use it to help you select decisions that you come up with. And then maybe with ChatGPT becoming good, could we ask, like, give me emails with high engagement? And some issues with doing this are if you have data from past marketing campaigns, you would like to incorporate that, but this doesn't really use that data. If you have existing human expertise, you may also want to incorporate that, like say you know certain features of text are really important. And also ChatGPT might say something inaccurate or inappropriate, and you want to control that. So our solution is to design a task very carefully where we fine-tune LLMs on results from past A/B tests in a way that augments human judgment, and it will provide a solution to the problems with just using ChatGPT by itself. The idea is actually quite simple. So if you have run an A/B test in the past and A did better than B, the basic idea of this paper is train an LLM to convert the worst decision B to the better decision A. And when it's time to make a new decision, the human first comes up with a candidate, and then the LLM improves on the human input. And notice in comparison to an LLM like ChatGPT coming up with marketing text or advertising text from scratch, this approach does reduce the risk of something going catastrophically poorly because we start with human input and try to improve it. And so the key question is, does this actually work? So we run a field experiment in an email marketing setting to show that it does work. And if given these results, then you can apply this framework to more complex settings. So the idea is, real quick, some background on email marketing. It's an important driver of traffic for e-commerce sites, and it's an important way to engage your customers. And the subject line of the email actually matters a lot. So holding fixed the content of the email, so say you have a sale or a new product and you want to tell people about it, how you phrase the subject line affects the rate at which people click on links inside that email, anywhere from 70 to 400% in our historical data. And traditionally, this requires a human expert marketer to write a subject line that's interesting but relevant so that you open the email and then click on something inside. And also, this is the task where we'll use AI to see if we can do better, but also adjust for things that might go wrong, like an AI learning to say things that are inappropriate because we tell it to maximize click rate. And our data comes from 10 years of previous marketing campaigns. about 20,000 past marketing campaigns covering about 300 pretty well-known brands. And in each marketing campaign, there were 16 variants of a subject line tested, with people randomly assigned to each subject line, and the sample sizes were reasonably large, and the click-through rates were recorded for each of these. So it's very good data. And an example of the fine-tuning task is on the left is a worst performing subject line, and on the right is a better performing subject line. And we tell a language model, convert this input to this output. And we do this for all the data that we have. So far I've been pretty agnostic about the mechanism behind what drives performance. This is like very data-driven in the sense that we just give raw data to the language model and tell it figure out what works. If you do have some idea of what does affect performance, so for example, say you know that the emotional valence mediates performance, you can impose that in this framework by adding emotional tags of the output to the input. So what this is saying is to the language model, here's a worst performing subject line. Generate for me a better performing subject line with this emotional valence. And so at runtime, a human expert can specify what emotions they want the output to have. Or if they're not sure, we can just try many different versions of this, generate all the outputs for different emotions, and automatically select the most appropriate one for the setting. So you don't necessarily give up the ability to control or impose some structure on this type of problem. But you don't need to do it if you're not sure. And so the basic decision-making flow is there's some context, like I'm running a sale next week, and I want to email my customers about it. Then a human or human assisted by a language model comes up with different ways to write this email. Then they use a predictive model, again, to sort these candidates by predicted click-through rate or other metric of your choice. And then the human makes the final choice. That the email gets sent out, and the results get recorded. And so we compare 3 different experimental groups. The first group, the human, proceeds as usual. And in the first experimental group, ChatGPT helps people improve on the subject line that they came up with. And in the second experimental group, our specifically tuned language model helps people improve on the subject line they came up with. So this doesn't test subject lines that are created from scratch by language models. People were a bit reluctant to try that. This was run last year, so at least this is the first stage, is whether language models can add value on top of what humans can already do by themselves. And so the results, we tested it in 36 email campaigns, real email campaigns. Sample sizes are pretty large. They were sent to 283 million recipients. And there's a 30% improvement in click-through rates from our tuned model over the control and the ChatGPT assisted version. And if you look at the distribution of outcomes across the email campaigns, so these are the CDFs, and the distribution of our model's assistance is shifted to the right relative to the control and ChatGPT assisted campaigns. And so what that means is for every percentile, we do better than the other 2 treatment groups. If you look at the distribution of raw performance, so this is, again, the CDF of control performance. So this is how well human subject lines did in click-through rates. You see an across-the-board improvement for every single email campaign by using our tuned model to help. And ChatGPT assistance doesn't systematically help performance, but it doesn't really harm performance either, at least systematically. And so that is some evidence in support of this design where the human inputs something first and the machine tries to help. So this does limit the downside risk. So at least for early stage stuff, this is like a good way to deploy AI assistance. And lastly, we did some auxiliary data collection. So we generated 1,000 subject lines from ChatGPT and our tuned model, and we asked marketing experts whether these subject lines could be used without any edits or not. And if not, what were the issues preventing these subject lines from being used? And so the orange bars are the problems with ChatGPT output. And you see the main issues are it says false or unverifiable things. So it will look at the content of an email and generate a subject line that contradicts something in that email. Or it misses information. So it just omits something that the expert thought was important. And the main issues with our model are that it says something unnatural. That's because we use a pretty small T5 model, and so that problem can be solved by using a bigger model. So, but notice it does a lot better on the fact check, the factual accuracy types of things. And so the main contributions of this paper are we showed A/B tests are a useful source of data for aligning language models. And we showed how to do this with a pretty simple framework. And we showed in a field experiment that it works, that it improves outcomes in a setting with real stakes. And the main takeaways are that language models are useful for these high-dimensional or unstructured decision-making types of tasks. So you can move beyond just using predictive models to sort through things you come up with your own. And you can actually look at what you've done in the past and systematically extrapolate insights on what's worked well and what hasn't. And so companies should, and other organizations should value A/B tests not just as a tool for, given this context, which decision should I make? If they do this many times, that's actually a useful strategic asset for improving decisions in the future. And so, again, this is just the start. I think there's a lot more to be done here. In general, it seems exciting that you can extend prescriptive models to more directly prescriptive ones with language models. And there's no reason why you can't use this approach for models that aren't just text. You could definitely do the same approach for images. So if you run different pictures in ads and see what works well, then you can train an image model to do something similar. Also, there's no reason you have to use A/B tests. So we use A/B tests because we know that the differences in outcome are causally due to differences in actions. If there's observational data where you can make similar causal claims, you could also use that here instead of A/B tests. So the scope of application is quite broad. And so with that, I'll take any questions. I also have more figures if people are interested. Yeah.
Were sales tracked at all after click-through?
It was unevenly tracked, and some of the brands don't really do sales. Some were like fintech companies offering student loan refinancing, so the observations of sales were really sparse. So we focused on something that was consistently tracked.
It should be correlated, right?
Yeah, it's correlated. Yeah, we checked the correlation in the cases where we did have sales, and it's decent. Yeah.
So it's a little bit technical question.
Yeah.
Very good job. I like the fine-tune process here.
Yeah.
So I was wondering whether you can open a black box, the hyperparameter. So if you build your own LLM like Llama, open source,
Yeah.
probably you can go. That will help you detect the mechanism.
Yeah.
You go to the attention head,
Yeah.
where the fine-tuned one with your 20K pre-test of all this A/B testing history.
Yeah.
So you can get the knowledge where the model doing right, because you can run this regression of this 20K campaign. You know what the text, what the sentiment to drive this click through, right, from the researcher perspective. Yeah. Then you did a large language model to know those rules.
Yeah.
The reason is because GPT have hallucination problem. They make up maybe some campaigns not well enough.
Yeah.
You do not know, right?
Yeah.
So if you want to know, you can go to the attention head,
Yeah.
and they help you detect that problem, and you know where's the source of your improvement of the lift, where it come from.
Yeah, that's the next thing we're working on. So we, you can look inside the language model and see intermediate variables that causally drive performance, and we can see what it's picking up on. We could see if it's picking up on spurious things that we don't want it to pick up on, prune those. So we're looking into that. There's some, I personally want to look at what drives output that's like not acceptable, that human experts say like this, we can't send this. And I want to see if pruning those, what drives that can lead to better like safety outcomes. But yeah, more questions. Yeah.
Building on Shuming's point, let's say we went back 2 years where large language models didn't exist, and you just built a supervised machine learning model where you used the characteristics of the taglines, and you optimized prediction there. How well do you think this would do compared to old technology?
Right. Yeah. So, which is not that old.
Right. That's why I put old in quotes.
Yeah. So you can like manually engineer some features like the length of the subject line, like the presence of certain words. That does like many texts are consistent with the features that are identified as optimal, right? It doesn't identify uniquely or super precisely what the text you should use is. So I think it would still require a lot more human judgment. And it's hard to, so I think it would definitely not be as useful out of the box because it would be the old process where the human has to basically, like the model says these features are important, and the human then has to like process that inside their head and write text that they think incorporates those insights from the model in some way. Whereas this is an alternative to doing that, and we think is more systematic. All right, last question.
Given the timing, were you using GPT-3.5?
Yeah. So it's
And what would you expect from 4.0, just given all the improvements in
Right.
areas?
So I think prompt engineering might be able to solve a lot of this, like saying false things problem. But I think it still doesn't know, like, it doesn't have access to our historical data. So the raw performance might still be better with fine-tuning a smaller model. I think I'm out of time. So thank you.
Thank you so much for your time. Today, I'll be discussing our paper, AI-Augmented Predictions, LLM Assistants Improve Human Forecasting Accuracy, co-authored by lead author Philip Schoeniger, myself, Ezra Karger, and Phil Tetlock. And our institutions are respectively London School of Economics, myself is MIT, Federal Reserve Bank of Chicago, and of course, Phil Tetlock needs no introduction. He is based here at the University of Pennsylvania. Disclaimer, the views expressed in this talk are solely that of the presenter, myself, and do not reflect the views of LSE, MIT, Federal Reserve Bank of Chicago, UPenn, or any other associated parties. Large language models are achieving an impressive degree of capability at an increasing number of complex cognitive tasks. For many of these tasks, the past assumption was that human cognition was strictly necessary for the achievement of these tasks, but this is starting to become less and less true with advanced LLMs approaching market competitiveness in various occupational tasks such as software development, customer service, and so on. We also have historical trends like Moore's Law and empirical scaling laws, which suggest that, just like they have so far, AI capabilities may very well continue to advance rapidly. And this is all happening, of course, in the backdrop of AI companies like OpenAI racing to build, quote, highly autonomous systems that outperform humans at most economically valuable work, unquote. This is OpenAI's actual mission, their definition of AGI as artificial general intelligence, as quoted in their actual charter. Intuitively, it seems that the skill of accurately forecasting future events, say in a domain like Russian politics, is fundamental for many human occupations, especially white-collar occupations. Consider, for example, that knowing beforehand that Russia was going to invade Ukraine would have been substantially helpful to all sorts of white-collar tasks, ranging from optimally trading oil futures to preparing the U.S. government's response to a then hypothetical Russia-Ukraine war. Researchers who want to investigate economically relevant capabilities in general and also of AI are thus led to the study of forecasting, arguably the purest form of which is the study of real-world predictions whose accuracy is incentivized by some skin in the game. A well-known example of this is financial markets, like the stock market, but the object of our team study was the perhaps more niche, at least right now, example given by prediction markets. So what are prediction markets? They are markets where people trade contracts that are paid out contingent on a certain uncertain future event occurring, such as before 2023, Russia invading Ukraine. The price of this corresponding contract aggregates many participants' forecasts of whether that uncertain future event will actually occur. And this aggregate forecast has time and time again proven to be quite accurate and arguably the gold standard of how to aggregate information like this. And this effect is known, this aggregation effect is known as the wisdom of the crowd, where the crowd is much better at predicting than any one person. This is why prediction markets, such as real-world forecasting tournaments, are so effective at helping achieve forward-thinkingness in political settings, sports setting, and at times, even economic forecasts. So the next question, given that we're at an AI in the Future of Work conference, is looking at how AI and state-of-the-art AI systems, large language models, can do forecasting. And there is a lot of early promising work like that of future search. And on the academic side, I would like to discuss the literature for LLM forecasting. It's a very new field, which was largely started by a collaboration between the lead author, Philip Schoeniger, and myself. Since then, other researchers have joined the field of LLM forecasting and made really vital contributions as well. To briefly go over the literature, it was well established by now that a single out-of-the-box large language model is quite bad when competing against humans in a real-world forecasting tournament. This was, the result of Schoeniger and Park 2023, which as far as I know, was the paper, the early paper in LLM forecasting as a field. And this finding has later been confirmed by other studies as well. Excitingly, in what can be seen as a replication of what I call the wisdom of the crowd effect, aggregating multiple LLM forecasts actually, helps you outperform, the base case. The thing to outperform first is chimpanzee throwing darts at a dartboard, 50% yes and 50% no. So at the very least, you should be outperforming that. And in fact, if you aggregate multiple LLMs and multiple LLM forecasts, you do outperform chimpanzee throwing darts. And in fact, you actually perform closely to the human crowd, which is the gold standard. So this was achieved by Schoeniger et al. With an ensemble of 12 models, and also by a fine-tuned ensemble of 6 instances of the same large language model by Holloway et al. At Jacob Steinhardt's lab at UC Berkeley. And just for a rough interpretation of how to put these findings in perspective, if you think here that manifold markets in the aggregate of this particular forecasting tournament, if you think that the human crowd performs around better than 90 to 95% of human participant in a given forecasting tournament, if you think 90 to 95% is that gold standard for the human crowd, then you could argue that an ensemble of LLMs can autonomously achieve something close to this. There's still a large way to go. The third author on this paper, Esther Karger, is better than 99.9% of human participants. So it's not at Ezra level yet, but it's still getting there. So there is room for improvement, although a lot of the gains have been made. So that's a lot of background. So let's go to the research question for this particular paper, which is not about autonomous LLM forecasting. It's about the question of, can AI augment human forecasters as measured by real-world forecasting tournaments? There are a number of motivations for this. One motivation, of course, is that LLM forecasting provides a window into the degree to which current and future models may disrupt human occupations, especially white-collar occupations that experts project to be especially vulnerable to disruption by LLMs. Another motivation is that unlike traditional benchmarks of AI capabilities like generalized reasoning, forecasting tournaments are less subject to the problem of overfitting, of something akin to a student memorizing the questions and answers on an exam before taking the exam, which is how they get a high score on the exam, even though they didn't actually understand the course material at a deep level. That can be possible for large language models as well, as long as the questions and answers of a given task benchmark are contained in the training data set. So in contrast to that, real-world forecasting tournaments are a very real test because the answers are not known to anyone, not even the human evaluator, until the future event happens or doesn't happen by the timeline. So arguably yields a robust test of capability of generalized reasoning capabilities. And the final motivation is that this allows for the study of capability gains from scaling via communication. So we have heard many times that scaling leads to capabilities in AI for large language models that are scaled more and more with more parameters, more training data set has led to AI capabilities gains via empirical scaling laws. Wisdom of the crowd is an example of how multiple different cognitive systems like LLMs or humans can lead to better predictions if you aggregate them. That's scaling by wisdom of the crowds. And here we study capability gains from scaling via communication, where just like if you have a human group, many humans communicate information. They specialize. they learn, preserve, optimize, and pass knowledge down from generation to generation. That's an example of scaling via communication by the human species. It's possible that a human cognitive system and an AI cognitive system communicating with each other can have a similar scaling capability gain effect. So that was the motivating research question. And the method was LLM forecasting assistant that was chat interface based on a certain LLM, and what that certain LLM is depends on the treatment condition. So it was a literal chat interface. And there were three conditions. Two of them were variants of LLM assistance based on the then state-of-the-art GPT-4 Turbo. There were two variants of this LLM assistant. The super forecasting variant, which emulated an assistant who was prompted to provide very high-quality forecasting assistance, and the biased assistant that was prompted to play the role of somebody who's very bad at forecasting and who would give very bad advice, very overconfident, biased. What is it? Extreme personal views are very, impact the advice very highly. This kind of cognitive biases. So these were two of the three treatment conditions. And the final treatment condition was Da Vinci 003 based the control group, Da Vinci 003, or as Ethan Mollick called it yesterday, a GPT 3.5 level model. Also not prompted to play the role of an assistant, just playing the role of a large language model was the control, so that we control for using the chat interface. And these 6 questions were the questions we used for the forecasting tournament. Everything from closing value of Dow Jones at a certain date to how many refugees and migrants will arrive in Europe, how many global, how many AI papers, how many commercial flights. Just questions with continuous answers were the answer type that we chose for this study. This was the data we got. One thing to notice about this data is that question 3 does look like an outlier. So for all the other questions, the three treatment groups actually, a lot of them are close. A lot of them are very close to 0 accuracy, which is optimal. So we did a lot of there was Windsorization, and there was division by the standard deviation for inter-question comparability. But 0, it's ultimately the starting base of the quantity is the absolute value between the given predicted answer and the actual answer that it turned out. So 0 is optimal. And in all but question 3, all the data points seem to be close to 0. But for question 3, a lot of people systematically got it wrong. And also the biased LLM assistant had the effect of making everyone less wrong, but in a way that is away from the collective belief. So it was very unusual, and I think we did a lot of analyses that were not pre-registered, exploratory analyses. That seems to question 3 was an outlier, and this kind of made a clean story difficult to present. So instead of presenting a clean story of we pre-registered these null hypotheses, these analyses plans, these are the results, I'm going to do something a little bit different and just talk about some findings, some patterns that I myself personally found interesting and with potential applications and potential future directions. First pattern I personally found interesting was that both the super forecasting and the biased LLM assistant significantly increased human forecasting accuracy. If we throw away the outlier question, the super forecasting assistant increased accuracy by 43%, and the bias assistant increased accuracy by 28%. Statistically significant with respect to our pre-registered analysis plan. If you don't throw away the outlier question, both assistant variants, we had a coincidence that both assistant variants increased accuracy by 23%, which was statistically significant. The second pattern I found interesting from our data was that there was no clear picture for the effect of both LLM assistants on the human crowd's forecasting accuracy. So remember, the main value of forecasting tournaments is not any one person's forecast, but like the crowd's aggregate forecasting accuracy. So in some sense, this, in terms of the public value rather than the private value of this technology of forecasting tournaments, we do want to, and I guess markets in general, we do want to look at the effect on the crowd's aggregate estimate. And on this, if we throw away the outlier question, so what we did here was we ran a pre-registered bootstrap analysis on the median forecast, which represent the aggregate forecast for each condition. And if we throw away the outlier question here, we find that the super forecasting assistant slightly increased the human crowd's aggregate forecasting accuracy, but the bias assistant significantly decreased the human crowd's aggregate forecasting accuracy. The confusing part is that if we follow the pre-registered analysis plan, if we don't throw away the outlier question, then still the super forecasting assistant slightly increases the aggregate forecasting accuracy, but the bias assistant actually significantly increased it instead of significantly decreasing it. So we just felt like there was just no clear picture we could get from this. And at the very least, it opens up the possibility that the private gains, the private benefits from applying large language models to forecasting, for example, the individual stock trader, could be a very different situation from the public societal benefits, of market making effects from having real competition to see who gets the most accurate predictions at about the price of a given stock. Market making effects are public benefits, but maybe this opens the door for the private benefit being positive, but the public benefit being less positive. And the final pattern I found interesting was that something Ethan Mala calls the escalator hypothesis was true, which is both LLM assistants increased the human forecasting accuracy at the relatively high and low skill levels by amounts that were without significant difference. So, both low skill and high skill were increased at similar levels. This contrasts with what is arguably the field's current consensus, the leveler hypothesis, where this was found in management consultants, customer service support agents, creative writers, office workers, law students, and programmers. At least, in the current consensus, this leveler hypothesis of relatively low skill workers are helped catching up by LLM augmentation. At the very least, this shows that it's a different story may be possible, at least in certain situations. So some future directions for research given this. Direction one, do it better. So seek greater statistical power, more participants, more types of conditions, optimize prompts, more LLM types, and fine-tuning. Combined approaches have both binary questions and the continuous questions. Direction two, develop theory, so construct parsimonious mathematical models to causally explain empirical puzzles from plausible first principles, such as when the leveler hypothesis is true versus when the escalator hypothesis is true. And final future direction is apply AI forecasting to augment human workers in the real world, such as in the white-collar occupations. Hopefully we augment rather than replace the workers in these occupations. So thank you so much for your time, and these are the references. I'd be very happy to hear your questions.